So in this question, we're asked to find the work done in moving a particle from the point P, 3, negative 1, 0, to the point Q, which has coordinates 2, 3, 1, if the magnitude and the direction of the force is given by F with components 5, 6, and negative 2. Assume the magnitude of the force is in pounds and the magnitude of PQ is in feet. And then I said, hint, find the distance vector, the displacement vector, you could also call it PQ, in component form first. So, okay, so let's take advantage of that hint there. What is PQ in component form? So what's the thing to remember? You take, okay, this is the tip. Q is the tip, right? P is the tail, so tip minus tail. Yeah? What's that going to be? 2 minus 3, negative 1. 3 minus a negative 1? And 1 minus 0. 47. All right. So there, you have like 3 formulas to choose from, you guys. But there's one that's heads and shoulders above the rest as far as ease of use. So what were the work formulas? So if we had a force vector projected onto a displacement vector, which we often called PQ, or V, then this guy here, I'll do it in green, is your projection of F onto PQ, right? Does that ring a bell? And then what is force? Force is, I'm sorry, what is work is what I meant to say. What is work? Work is the force in the direction of motion times the distance that you move the object, right? So the first formula we came up with then was we took the magnitude of the vector in green. To get work, we took the magnitude of the vector in green, so that's the projection of F onto PQ, and that would be the amount of force applied in the direction of motion, wouldn't it? And then what's the distance that the object is going to be moved from point P to point Q? So that would be magnitude of PQ. And then, I don't mean to derive all this over again, this is what you saw in the lecture the other day, but a little right triangle trigonometry will convince you that this is the same thing on the right hand side here as what? It involves the cosine, right?
Magnitude of the force vector times the cosine of theta.
So magnitude F, almost. Magnitude PQ, don't forget that's still here, right? You were just talking about the magnitude of the projection of F onto PQ. That's true, but for everything, don't forget to include the magnitude of PQ, and then times the cosine of theta, right? You're not going to want to use either one of these formulas. It's the third one you're going to want to use. What is the second formula equivalent to? Well, all of them are equivalent to F dot PQ. So that's what it breaks down to then. We're just going to say work is equal to force dotted with PQ, which is the vector 5, 6, negative 2, dotted with PQ, so negative 1, 4, 1. And what's that going to turn out to be? So, okay, so let's show some work here. So multiply the first components together. What do you get? Negative 5. The second components? Plus, right? Third components? Minus 2. So it's 24 minus 7? Or 17? 17. Okay, let's get the units right. Foot-pounds, right? You were told the magnitude of the force is in pounds. PQ is in feet. You better put the units down. Foot-pounds. That's it. So this is the only work you need to show. It's a really quick problem.